with that, Niv, stage is yours. And yeah, please go ahead.
Okay, so thanks again for having me. Okay, so as Andreas said, I'll present two papers about filter data structures and how to expand them efficiently. But first of all, what is a filter?
If, sorry,
Yeah,
it's
yeah.
just us, but we were kind of hearing Andreas loud and clear, but your voice is a bit kind of blurred. So maybe,
Okay,
yeah, now it's much better.
okay. So I'll just speak more clearly and close to the computer, I guess. Okay, okay. So first of all, and do let me know if you can't hear me throughout, so I can adjust. Okay, first of all, what is a filter? So a filter is this compact probabilistic data structure.
And sorry to interrupt again.
Yeah,
Anupam, could you please mute the room? There's a bit of background noise. I'll also mute ourselves now. So with that, Niv, please start again if you like. Sorry about that.
no problem at all. Okay, so a filter is this compact data structure that represents keys in a set and allows you to answer set membership queries. So in particular, a filter cannot return false negatives, but it can return false positives with a tunable probability. So let's see. Okay, so why use a filter? So filters are typically used when we have data stored across a memory hierarchy. Imagine we have a lot of keys, data keys in disk, and we want to check for the existence of a given key. Well, what we can do to speed this process up is store a filter that represents that data set in memory and check the filter before we check the data in storage, whether the key exists. Now, the filter can say yes or no. If it tells us no, that's perfect because we get to skip an expensive storage access and save performance. And that's really the core use case of filters within systems. It's really to help us save storage accesses or network hops or kind of expensive system checks. However, because the filter is an approximate data structure, it can return false positives. And generally, we call the false positive probability of the filter epsilon. And false positives is really the thing that we're trying to minimize because with a false positive, right, you end up doing the work that you were trying to avoid, but you're doing it redundantly, right? So with a false positive, we go to storage, search for a key that doesn't actually exist, and so we waste performance. Okay, and in addition, another important property, filters do not return false negatives, meaning that if you're searching for a given key and the key exists, the filter will always return a positive and will actually find the key we're looking for. Okay, so these are the basics. Now, all traditional filter data structures and they've been around since the early 70s. Traditionally, they're allocated with a fixed capacity in advance, right? So from the very beginning, you know how many keys you're going to insert into that filter. And as long as you don't exceed the number of keys that you initially plan to insert, the filter will give you a guarantee over the false positive rate and over the cost of insertions, queries, and even deletes if the filter supports deletes. Okay. However, in many applications, the data size is growing, and we don't actually know what the data size is going to be when we're first allocating the filter. And this begs the question of how to expand the filter efficiently with respect to the data size, while ideally also maintaining good false positive rate and performance properties. So that's the problem that we're trying to solve here. And this problem has many applications, right, in all areas of systems, in architecture, networks, and OS, and specifically in databases. This problem of needing to expand a filter can arise in when we're trying to compute joins or in key value stores, right, where we have filters to prevent storage accesses and we don't know how much data is going to grow. Okay, so everything so good so far? Any questions about context? Okay. So the traditional filter, that's the Bloom filter. It's the first filter ever created in the 70s. And this is a fun picture that I actually found in a cafe in Copenhagen. This is a coffee filter, and actually it has a brand of Bloom. So this was like a pretty remarkable coincidence, I thought, and I thought I'd share that. but also just a coincidence. The way that the Bloom filter actually works is it just consists of a bunch of hash functions and a bunch of bits in a vector. My talk is not really about Bloom filters, but I'm just covering them very quickly to motivate the problem. So to insert a key into a Bloom filter, right, we just hash it using a bunch of hash functions into a bunch of random bits in a bit vector, setting those bits from zeros to ones, or keeping those bits set to ones. Because of the way this data structure works, it's actually not expandable. The reason it's not expandable is because you could have multiple keys mapping to each individual bit in the bit vector. And so when you're trying to expand this thing, you might imagine trying to allocate a larger bit map and trying to reassign each one of the bits set to ones to some, location in the larger bit map. The thing is, multiple keys might have mapped to each one of the ones here. And there's no way to disambiguate that. So, really because of that, there's really no way to efficiently expand Bloom filters while, without introducing false negatives. Okay. And actually for that reason as well, Bloom filters don't support deletes. Okay, so there are various workarounds to the filter expansion problem. And let's look at a few of them. So one workaround is just to allocate a very, very large filter in advance. But that's not great because that means that we're allocating a lot of memory before we know that we're even going to use all that memory, right? So that's an obvious downside. The other thing that we can do, and that's maybe the most common workaround, is to, whenever we reach a particular size for the filter or capacity, just throw away that filter and reconstruct a larger filter from scratch. And we can do that by scanning the data, right? Scanning the data and just, rehashing all the keys and doing all the work again. Right, but that's going to require a full scan over the raw data, and the raw data may be in storage or over a network. So this is going to be quite expensive. Ideally, we want to enlarge the filter without doing that large scan over the original data. Okay, so now I'm going to explore 3 different solutions to this problem. The first two, chaining and fingerprint filters, this is mostly problem analysis. We'll maybe try to do that in 10 minutes-ish, and then I'll get to InfiniFilter and AlFilter, which is really the bulk of our work. Okay, so we have a pretty thorough problem analysis. Any questions so far about context, motivation? Okay, so chaining. The idea with chaining is to say whenever the filter that we have runs out of capacity, let's just allocate a new filter that's 2 times as big while keeping all the other filters that we've created still intact and existing. Right, so whenever we're out of capacity, we'll allocate the new empty filter, and good. All insertions of new data can go into the largest filter that we just allocated. But there's a clear downside here. And the downside is that queries now actually have to search each one of the filters in order to find a given key, right? So okay, so one advantage to this approach is that this is actually going to work with any kind of filter that you can imagine, right? It really abstracts out the details of the filter, right? But the downside is that queries now have a logarithmic cost because we have a logarithmic number of filters in a chain and we have to check all of them. That's not going to be great for our CPU overheads. Okay, we might also ask, what's the impact on the false positive rate? And here things actually get kind of interesting. So, you could say, suppose that we actually set the same false positive rate to each one of the filters in this chain. Well, so we can do that. And then if we, add up all of those false positive rates across all the filters to compute, to reason about the overall false positive rate, right? We see that the false positive rate ends up being logarithmically increasing as well, which may not be great, right? It means that it deteriorates over time. Okay, so then you might ask, suppose we want to actually maintain a stable false positive rate as we, expand and create these new filters. Well, what can we do? Okay, so here I would normally ask people to raise hands and give ideas. Does anybody have an idea? It's a bit more complicated when it's virtual. Okay.
I mean, we could increase the precision of these new filters.
Yes, excellent. That's exactly the right idea. So what you can do is set lower false positive rates to newer filters. And then you might ask, at which rates should I actually increase their precision? And the most natural approach that will probably come to anyone thinking about how to solve this is just, why don't we just half the false positive rate for each new filter that we're allocating? Meaning the false positive rate will be geometrically decreasing. This will, kind of trivially get rid of that log n factor and make the overall sum of these false positive rates converge. What's the issue though? The issue is going to be memory. So, so in particular, we can analyze the memory footprint for this whole thing by looking at how much memory the largest filter is taking up, because it's the largest, but it also has the smallest false positive rate. And there are ways of analyzing this, and I won't really get into all the details, but basically, the following expression is a good summary of the number of bits per entry that you need for the filter at the largest level. And if you kind of, simplify that, you end up with the following. So with this kind of approach, geometrically decreasing false positive rates, you need log n number of bits per entry, in addition to just, the initial number of bits per entry that you started with for the filter. Okay, so that's not great, and we want to ask, can we achieve, can we stabilize the false positive rate using a better memory footprint? And okay, so so ideally the false positive rates should decrease more slowly but still converge. And happily for us, we can actually still do that. And it was a little bit it was kind of surprising for me when I found out that this is possible. But you can, so what you can do is actually get the false positive rates to decrease polynomially according to the following series. This series is the reciprocal of square numbers, right? So, right, you should be able to see the pattern. You just 1 minus 1 over wherever you are in the series squared. And this series actually turns out to converge to a constant as well. And this was solved for us by our friend Euler in 1734. And this series happens to beautifully converge to pi squared over 6. Okay. So, and that's just 1.6 something. Okay, so what you can now do is get the false positive rates to decrease polynomially according to this theories, and you are guaranteed that your false positive rate is still going to converge to a constant. But now, because these false positive rates are actually decreasing more slowly, right, you can analyze the number of bits per entry that you need for the largest filter. It's going to be the following expression. Never mind the math so much, but if you then simplify this expression, you end up with log n. Okay, so that's much nicer than the log n that we had before. Okay, and we're still managing to hit the same false positive rate target. Okay, so it actually turns out that this expression here is pretty close to, it turns out that there's a lower bound for how good you can be with respect to memory footprint for expandable filters. This comes from a 2013 paper in Fox, and this is actually pretty close to the lower bound. And the difference between these approaches is actually pretty significant in practice, right? So, so if you're geometric, you're actually increasing rapidly in memory as you expand. If you're polynomial, this is a lot more stable. Okay, good. So far we've analyzed chaining. We actually saw that the false positive rate versus memory trade-off we can achieve is pretty reasonable, but actually the main problem was queries. Queries are logarithmic. So now let's have a look at fingerprint filters and see how much better we can do. Okay, so any questions? Okay, yeah, maybe it's better to just keep questions till the end. Okay, so what are fingerprint filters? So this is the second kind of approach in our problem analysis. So fingerprint filters is a new family of filters that emerged over the past 15 years as an alternative to Bloom filters. They offer various advantages. Here's roughly how they work. What you're going to do with these fingerprint filters is hash every key into two components. One of these components will be the address of a slot in a hash table, and the other part of the hash is going to be just a fingerprint. All right, so you generate this large hash, you partition the hash into these two components. And then what you do and we refer to the whole hash here as the mother hash. And the mother hash consists, right, of the slot address and the fingerprint. Okay, and then what we'll do is we'll take the fingerprint part of the hash and insert that into the corresponding slot, right? That's also, part of the hash. Right, so now the fingerprint is in that particular slot. And now whenever we have a query, right, so, a query for a given key is also going to hash that key, generate a slot and a fingerprint, go to the corresponding slot in the hash table and check whether there's a fingerprint match. And if there's a fingerprint match, it's going to return a positive, and otherwise it's going to return a negative. Right, so this is how these filters work in a really broad level. It's just a hash table of fingerprints where fingerprint is a hash digest. Okay, now, what is generally the false positive rate with these schemes? It's something like 2 to the power of minus the fingerprint size. Let's call the fingerprint size F. And the number of buckets in the scheme is 2 to the power of the size of the address. Okay. Okay, so various filters of this kind of family have been proposed over the past decade, and they mainly differ in the collision resolution strategy. So that, so inevitably, whenever you're doing hashing, there are going to be multiple fingerprints mapping, going to the same slot. You need to resolve that somehow using a collision resolution strategy. Different filters in this family mostly differ with respect to the collision resolution strategy. So for instance, quotient filter will do something like Robin Hood hashing, XOR filter does something, technique called peeling, and cuckoo filter does cuckoo hashing to resolve collisions. But for this presentation, we're actually completely going to abstract out the details of collision resolution because the techniques that I'm going to talk about are actually applicable regardless of the collision resolution strategy. Okay, the promise with respect to all of these filters is that they're actually semi-expandable. So they don't fully solve our problem, but they offer some promise, and we're going to be able to build on that promise. Okay, so here is why they offer promise. So what you can do with these filters is you can basically take every fingerprint and concatenate every fingerprint in the filter, concatenate it with the slot address that it resides in. That allows you to derive the original hash of the key. And what you can now do is basically, right, you see here, this is the division point between the address and the fingerprint. What you can do is just kind of slide that. So basically what we're doing is we're stealing the most significant bit of the fingerprint and we're taking the least significant bit of the fingerprint and reassigning that to become the most significant bit of the address. Okay, why is that good? That's good because we can now take this hash and insert that into a new filter that's larger by 2x. Every slot's going to be narrower by 1 bit because we sacrificed 1 fingerprint bit. But the number of buckets, but we can now support twice as many buckets because all the addresses are now larger by 1 bit. Right? So this thing does allow us to expand, but there are issues with this approach. Right, so we can expand here without rereading the original data, but there are 2 issues. And I'm sure some of you will have picked those up yet. But the first issue is really with the false positive rate. What's happening is because the fingerprints are shrinking and shrinking and shrinking as we expand, basically with every expansion we lose 1 bit. That means that you actually end up with the following false positive rate expression for right. So we're losing. So this is the number of expansions that happen, and for each expansion we lose 1 bit. That's why we get this expansion for the false positive rate. And if you simplify that, you actually end up with a linearly growing false positive rate. So that's really not great. And the other problem is that eventually your fingerprints completely run out of bits, and at that point you cannot continue expanding. So basically, these filters support only most F expansions, and when you've expanded this many times, the filter at that point is useless because you have 0 length fingerprints and you can no longer continue expanding. So not great. It's something, but it's not great. And I would say that this is actually in some sense the state-of-the-art approach, right, before our work. Okay, one thing that you can do is actually set a larger fingerprint size from the onset, but this is just going to delay the problem, right? It means that you're going to be using more bits per entry from the beginning, but then, you're just delaying the problem. Eventually, you will still run out of bits if you expand sufficiently many times. Okay, so here's kind of our problem summary so far. We have chaining. The problem with chaining is Fourier cost, which is logarithmic. Whereas with the fingerprint filters, we have a linearly increasing false positive rate, and they only support a limited number of expansions. So with those, those two baselines, here's our research question. And the research question is, can we expand a filter indefinitely without scanning the original data, and while best scaling the cost of queries, insertions, and deletes, the memory overhead, and the false positive rate? And we want the best trade-off between all these metrics kind of at the same time. Okay, and now I'm actually finally getting to our work. So this is InfiniFilter, and this is from Sigmod 23. Okay, and in this paper, so InfiniFilter is actually also, it's based on these fingerprint filters. It's also just a hash table of fingerprints. But the core innovation is that the fingerprints can actually now have variable sizes. And I'll talk about how we support them, but why do we need the fingerprints to be variable sized? Well, so here's why we need that feature. During expansion, we're still going to sacrifice one bit from every fingerprint and reassign that to the slot, like to the slot address, to be able to expand. But now the fact that these fingerprints are variable sized means that after the expansion, we can actually set, fingerprints that are still as larger as before, or even larger, to prevent the overall false positive rate from decreasing and decreasing. Okay, so that's really the core insight. So older fingerprints are still going to be shrinking. We can't do anything about this. But newer entries that we insert get larger fingerprints. And this is why we need the variable length fingerprints. And okay, so that's the core thing. Let me now tell you how we actually implement this. Because you might say, okay, with variable length fingerprints, right, they have variable lengths. How do we actually align those within slots of the hash table? So here's how we do that. So every slot is now actually going to consist of two fields. So the first field is going to be what we call the unary age counter. So the age counter is basically counting how many expansions ago a given entry was inserted into the filter. So if this is 0, it means that this entry in the slot was just inserted. No expansions have taken place since. If this is 1,0, it means that the entry was inserted 1 expansion ago. If it's 1,10, it means it was inserted 2 expansions ago, and so on. Okay, this is the unary edge counter is always finishing with 0, and that's the limiter, right? So when you see the 0, you know that whatever is coming next is the fingerprint. So this allows you to uniquely parse the slot. Okay, and the rest of the bits just belong to the fingerprints, right? And this is right, and this is basically what allows us to but this allows us to store variable length fingerprints in the slots. Okay, right. So overall, this is fixed length. And why is it fixed length? It's fixed length because every expansion, the fingerprint loses 1 bit and the age counter gains 1 bit. So the overall sum of bits in the slot stays the same. Okay, so here is, just to make this a little bit more concrete, here's how we actually handle an expansion. So here's a simple example. So this is an entry that was just inserted because we can see that because the unary age flag is 0. This is the fingerprint and this is the slot address. So here's how we're going to expand. So during expansion, here's what we'll do. We're going to take the least significant fingerprint bit and reassign that as the most significant slot address bit in the new filter. So this is the address in the new larger filter. We are then going to store all the bits of the fingerprint except the one that we sacrificed as the new fingerprint. And we will increment the unary age counter by 1, which means it's now 1,0. Right? So we just repeat. So by repeating this process for all fingerprints in the original filter, we achieve expansion. Okay, good. And now remember that the core point of this is that even though this fingerprint shrank due to the expansion, new fingerprints inserted after the expansion can be set fingerprints that are as long as before or even longer. Okay, and why is this good? So let's now try to analyze the false positive rate with this approach. Everybody with me? Any questions? Any complaints? Okay. Okay. So let's try to analyze the false positive rate. Okay, so with this approach, so the filter is expanding by a factor of 2 every time. And this means that half of all the entries in the filter actually have the maximum fingerprint length, right? A quarter of all the entries have a fingerprint length that's shorter by 1 bit. An eighth of all the fingerprints are shorter by 2 bits, right? Et cetera, et cetera, et cetera. So basically what I'm trying to say here is that the fingerprints actually follow a geometric distribution where most of them are long and fewer and fewer and fewer of them are short. And what you can then do, and I'm not going to get into the detailed analysis, but if you take the weighted false positive rate across this distribution of fingerprint lengths, you actually end up with the following false positive rate. You end up with false positive rate log n, basically a logarithmic false positive rate. And note that this is much better than what we had with the regular fingerprint filters that I showed in the problem analysis, right? There, the false positive rate increased linearly. Here, the false positive rate is increasing logarithmically. So that's much, much better. It's still not perfect. We still don't like the fact that this log is there. We would prefer this to be constant, but it's already a big improvement. Okay, good. So now suppose that, we want to get rid of that log n factor as well, because, we just want to guarantee a stable false positive rate to our application. There are two things we can do. The first one of them is this is a bit application dependent, but in many applications, after you query the filter for the existence of a given key, you actually then go to storage to retrieve the original key. And if the key actually exists and you retrieve that key, you can just rehash that key and enlarge the fingerprint that corresponds to that key if that fingerprint had shrunk. Right? So we call this a rejuvenation operation. And this works in applications where you actually have queries that target older keys whose fingerprints have shrunk. And this can work pretty well in practice. Okay, I hope that makes sense. However, this method is still limited. It's limited because this method relies on you having queries in the workflow that are targeting older data. So you might ask, can I have a method that's independent of the query workload that still allows me to stabilize the false positive rate? And the answer is yes. So the other thing if you don't want to rely on query workloads to stabilize your false positive rate, you can actually use the trick that we saw from training of increasing the precision. So what we're going to do with this trick is we're going to set the slot width to slightly increase as we expand, right? And if we set the slot width to expand at a rate of log n, that's kind of what we saw with chaining when we were, polynomially increasing the precision. So we can actually apply that trick in this context as well. And just to give you an intuition of how the analysis, plays out here. So if we're setting even longer, slightly longer fingerprints every time that we expand, and we set them to slightly increase by a rate of log n, right? That log n term, kind of comes here, right? Because it's, contributing to the fingerprint length. And then that causes that log n term to cancel out. Okay? But so this method of stabilizing the false positive rate is independent of the query workload, but it's going to cost us more memory. It's going to cost us log n more memory, which, is okay. And actually turns out to be the best that you can do based on the lower bounds that we know. Okay, so basically you have these two methods, right, of stabilizing the false positive rate. And here is, just kind of a crude comparison of these false positive rates. So in this experiment, you're measuring the false positive rate as you increase the number of entries in the filter on the x-axis. And so the false positive rate for the traditional fingerprint filters is linearly increasing. For InfiniFilter with fixed length slots, the false positive rate is logarithmically increasing. Right? And then if you use the trick with slightly growing slots, you can actually completely stabilize the false positive rate. It just becomes constant, but you're spending more memory, log n more memory. Okay, so these are the kind of trade-offs that you can deal with. So basically so you can control whether you want a better false positive rate or a better memory footprint by choosing between these two schemes. Okay, good. Andreas, at which point would you like me to finish and allow for Q&A?
Maybe in around 10 to 15 minutes.
Okay, I think that's totally fine. Yeah, so we leave like 10-ish minutes at the end. Okay. Okay, let me talk a little bit about deletes. So deletes are a bit more complicated with these expandable filters. Let me give you a hint about why. Suppose we're trying to delete a key. Usually the way that you delete a key in one of these fingerprint filters is you just go to, right, you hash the key, you go to the corresponding slot that contains, contains that key, and you find the matching fingerprint and just remove it. And this is of course predicated on you removing a key that you actually know exists. Okay, but with these kind of expandable filters, they complicate deletes. And the reason that they complicate deletes is because you can now have variable length fingerprints in these buckets. So suppose that you're trying to delete key X might actually match multiple keys with different fingerprint lengths in a given slot. So that begs the question of which one of them to remove. I won't go too much into this, but just I'll just say what you wanted. So we're tempted to say that we want to delete the shorter fingerprints, right? Because it's shorter, shorter fingerprints deteriorate our false positive rate. But it actually turns out that if you remove the shorter fingerprint, you might end up with false negatives afterwards. And the reason is that the shorter fingerprint might correspond to some other key, right? And if you then actually query for that key, and the key happened to be, different along, the more significant bits that you didn't actually have there materialize because you lost some bits, you might get a false positive rate, or you might get a false positive. So right, I'm kind of glossing over this, but basically, as long as you always remove the longest matching fingerprint, you're guaranteed to actually always be okay, because the shorter fingerprint will still match whichever key you didn't remove. So basically, okay, so the bottom line point here is these filters are, if you're using this trick, these filters are not just expandable, they also support deletes, which is nice, right? So they're fully dynamic. Okay, so now I want to talk, I'll introduce some other problem, motivate Aleph filter. I hope you're not too tired. We're actually almost done. Okay, so here's another problem. So suppose we're using infinity filter and we expanded F times. Where F is my original fingerprint size. After the first F expansions, the oldest fingerprints in the filter actually completely run out of bits, right? So, and when they completely run out of bits, right, the unary age counter will actually occupy the entire slot. You can see that because this is all ones, and then the delimiting 0 is all the way at the end. We really have lost all fingerprint bits here for this particular entry, right? And so we refer to these as void entries, right? So for void entries, we lost all fingerprint bits. And the thing with void entries is whenever a query actually happens to land on a slot that contains a void entry, we don't actually have any fingerprint bits to do any filtering. So that query will always return a positive, okay? Okay, so the real problem with void entries, though, is that once we start having them in the filter, there's a question of how to continue expanding. Because when we have a void entry, we no longer, right? Our whole method of expansion relies on stealing bits from the fingerprint and reassigning them to become a part of the slot. But with these entries, right, we have completely lost. We don't have fingerprint bits anymore, so we cannot sacrifice them and reassign them to become a part of the slot address. Okay, so so the way that InfiniFilter handles this is it actually removes these void entries from the main filter and actually stores them along a series of smaller filters. And I'm not going into the details. I'm just trying to motivate the problem. Right? So we're removing these entries and storing them along a series of smaller filters, smaller instances of the same thing. Each one of these is an instance of a smaller identical data structure. But of course, you're going to say, okay, didn't we just reintroduce the problem that we had before with chaining? Now we have a series of filters that we have to access. Well, not quite. This is actually the guarantee that we get for queries. So the time complexity we get is log n divided by f, where f is the fingerprint size. The main intuition here is that each one of these filters actually stores, multiple generations of entries across different expansions within the same filter. So the overall number of filters here is actually it's much smaller than with chaining, but it still leaves something to be desired, right? Like we still wonder, like, can we actually just get constant time? Because it's nice to get constant time if we can. Okay, and that is really the motivation for Aleph filter, which is the paper that we had in VLDB last year. Okay, so with Aleph filter, the core new innovation is we're still actually going to be, taking these void entries and storing the full hashes along a series of smaller filters. But in addition to that, here's a new design decision. We're also going to duplicate these void entries within the main filter. So I'll show you what I mean by this. So here is a filter before expansion, and we have a void entry here. So now, in order to expand, right, we can do that for these 3 fingerprints as before by just reassigning 1 fingerprint bit to become a part of the slot address. How do we expand the void entry? Well, aside to also recording its hash in a smaller filter, what we'll also do is duplicate the void entry to take up 2 slots in the expanded filter. Why? And in particular, we map the void entry to both slots that it could have mapped to if there was an additional fingerprint bit to sacrifice. All right, so basically, it's kind of like a brute force strategy. We're basically putting it in all possible slots it could have gone to. And this is good for queries because now we can guarantee that when we're querying for a given old key, whichever slot that key actually goes to, we can guarantee that because of that duplication of the void entries, it will always hit a slot that actually has a void entry and return a positive. So basically, this allows us to make sure that we never get false negatives. If we're querying for an old key, we still will always return a true positive. Okay, and that actually also means that we can get queries in constant time, because now all the relevant information that we have to process queries exists in the main filter, right? So if we're querying for newer entries, we'll actually match, existing fingerprints. And if we have a query to an older entry, well, it has a void entry that was duplicated multiple times across the filter. And so we're going to find that void entry in constant time and also return a positive, right? So all queries finish in constant time. Now, in the paper, so a natural concern here, right, you might say, how much space do these void entries take up, right? They might inflate the size of the filter, they might blow it up. You can actually show that they take up a moderate amount of space, negligible in some cases, moderate otherwise. You can deal with the amount of space that they take up. Right, this is also something I'm slightly glossing over, but right, details of that are in the paper. Okay, but the main technical complication that these void entries actually introduce, this is probably the last problem that I'm talking about in this presentation, so hold your breath, I'm almost done. Suppose we're now trying to delete an old key, right? This is a key, so if it's an old key, it's, it might actually contain multiple void entries across the filter. So this begs 2 questions. The first one is, which void entries to remove for that key? And so how do we identify all the void entries that actually correspond to that key we're trying to remove? But then the second question is actually how to do this in constant time, because like the whole point of this paper is to do things in constant time. And you might say, okay, it seems impossible to do this in constant time because there are multiple void entries I have to remove. So how do we do this? Okay, let's tackle the first question first. How do we remove this entry in constant time? Well, it's cheating, but it's not really cheating. To remove the entry in constant time, we actually just go to, we hash the key that we're trying to remove. map it to a given slot, the slot that the key would actually correspond to, and actually just replace the void entry in the slots by a special character string that we call a tombstone, right? The tombstone ensures if we query for this key again, we're still going to go to this slot because this is the slot that actually should contain that key, and we're going to find a tombstone. And if we find a tombstone, we can return a negative, right? So this is good because now, right, subsequent queries can return, right? They can say that the key doesn't exist if we deleted it. So that's in some, okay, and in addition to that, right? Okay, so that's still not ideal because, you know, all these void entries that actually correspond to the same key, they still exist in the filter. So eventually we want to remove those. So to be able to remove those eventually, we also add that key to, you know, a deletion queue. And then during the next expansion is when we're actually going to remove these void entries that correspond to that key. And again, here I'll gloss a little bit over the details as well, but basically we have these, you know, kind of other auxiliary data structures that allow us to store the original hashes of, you know, older entries. And by, you know, kind of looking up the original hash of this key that we're trying to remove, and basically by checking how long the hash of this key is relative to the current slot address size of the filter, we can actually infer how many times that, you know, the void entries for that entry were duplicated. And that actually allows us to remove all the void entries for that entry without introducing any false negatives. Okay, so I hope that gives you a bit of intuition. I know that I didn't really go through all the technical details here, but basically, hopefully you got the message that right, we're duplicating these void entries to allow us to still achieve constant time queries, but then there's a question of how to properly delete these void duplicates if we're trying to delete an old key. And hopefully here you get the sense that this is actually possible. And it's possible to do that in constant time using tombstones, and it's possible to then remove all the corresponding void entries in constant amortized time as a part of the next expansion. Okay. So I think that's actually all I wanted to, okay, so here's just a performance figure so that you can see that if we're measuring query cost, AliFilter allows you to achieve a better query cost than InfiniFilter, and this is because it's constant time, right? With InfiniFilter, you have to traverse a chain of data structures. With AliFilter, it's just one data structure. Latency is still increasing here because of just caching effects, right? The thing is outgrowing the cache. So that's why you see the increase here, but it's still better. Okay, so here is the conclusion. We introduced these two papers, InfiniFilter and AliFilter, and they allow you to infinitely expand filters as the data size grows. You can expand these filters without rereading the original data. As you expand, they allow you to maintain a stable false positive versus memory trade-off. And actually, they allow you to achieve the optimal false positive rate versus memory trade-off according to well-known lower bounds. And if you're using AliFilter, you can also do constant time queries, insertions, and deletes. So you're fully dynamic, and you're fully dynamic in constant time. Okay. Yeah, so, and why is all of this good? All of this is good, again, because, right, we use these filters to allow us to prevent storage accesses, right? So the fact that you have a lower false positive rate means fewer storage IOs, and the fact that this thing can actually answer queries in constant time means less CPU, right? So overall, the promise here is, you know, more efficient systems if we use these filters. Now, I just want to briefly advertise a bit of another thread of work that we have. This is just, will take me 30 seconds. So far I presented point filters. So these are filters that support only queries over single keys. However, in many applications, you actually want to issue range queries. So range query is a query for, you know, given two keys, tell me whether there are any keys in between them. If there is at least one key in between them, return a positive, and otherwise return a negative. All right, so these are range queries, and point filters don't work really well for them. Now, over the past decade, there has been a lot of work on range filters. And so we have two papers on this topic from 2025. One of them will be presented in Berlin in SIGMOD. The other one is actually conditionally accepted to VLDB, looking good. And I'm just going to tell you a little bit about the trade-offs that they offer to kind of show you what the space is like. So Memento filter actually offers you constant time queries and a really, kind of robust false positive rate. But the main problem here is that it's actually very hard with these range filters to support variable length keys and queries. And Memento filter does not allow you to do that. You can't support, so it's much more limited in its range of applicability. Then to overcome precisely this problem, right, we worked on Diva, and Diva is slightly slower, so it's log n in terms of operation cost, and the guarantee over the false positive rate is slightly weaker. We call it semi-robust. It's not as good as with this, but it's actually still practical for many workloads that we tried. And this does actually allow you to support fixed length keys and queries, right? So the problem of range filtering is more difficult, as I hope you can see here. But there are interesting trade-offs and things to explore in this space. And actually, interestingly, all of our work on expandable filters combines really nicely with these. So Memento filter and Diva are both also expandable by drawing from all the techniques that I talked about in this presentation. Okay. So I think that's it. And I think there's 10 minutes left. So thank you very much.
Thanks a lot, Niv. It's very insightful, and yeah, you seem to cover it all. It's very interesting. So actually, I would have a question regarding Aleph filter, like these void entries that you were talking about. You said there are not that many. Like, can you quantify that, like in percent? Because there might be some, other techniques you could do to further compress them.
Yeah. Excellent point. So I can actually quantify it. What's the best way to do this? Let's just go here. So let's go here to, let me just share the screen again. Okay, so yeah, just to remind everybody, right here are the void entries, and we're wondering how many of them actually exist in the filter. Okay, so you remember I mentioned that InfiniFilter and Aleph filter, they have two different schemes. One of them is where the slots stay fixed width, and one of them where you're actually increasing the slot width at a rate of log n. There's actually a difference. So the number of void entries is going to be different in these two schemes. If you're keeping the fixed slot width, the number of void entries will actually correspond to the false positive rate times log n. So it's not that much because you're multiplied by the false positive rate. The false positive rate might be something like 1%, but it's actually still logarithmically increasing. Now, if you're using that technique where you're using longer, you're enlarging the slots as you expand the filter, what happens then is actually, because fingerprints are longer and longer, the rate at which you create new void entries decreases. And that actually stabilizes the fraction of void entries in the filter to a fixed constant. It converges.
Got it.
So, yeah.
Yeah, okay, very interesting. I was just wondering if you could do a sparse representation, like just have an extra bitmap sort of indicating the void entries and then sort of rank compress, have a rank structure on it. But yeah, it might not be worth it if it's like you just described.
Yeah. I get you. I think it's an interesting direction so we've had some of these thoughts. Obviously, the downside with having a bitmap will be that you're spending 1 bit per slot. So this is a bit, but yeah, ideally we would have liked to just spend on the fingerprints to get the false positive rate down.
Right.
But then, as you say, there are tricks for bitmap compression, which I know that you've worked on. And that could be interesting to explore. I agree.
Yeah, and also like once you increase the fingerprint length of the new entries, that one extra bit that you require will amortize probably over time. But yeah, lookup time is going to be more expensive.
Yes, that's also true. if you have to decompress that bitmap.
I guess I'm not sure. Niv, do you hear us?
Yeah, I can hear you okay. If you speak maybe close to the computer, or I think it's okay. Try.
We have an owl here somehow. Yeah, but I was wondering, is there an intuition why you kind of for the newer entries you start with the larger fingerprints and then you reduce them? You could also think of other schemes, right? Where you do this not just based on age, but some other criteria. And maybe I missed that, but what is the intuition behind that?
So basically you're asking why are we setting longer fingerprints to newer entries?
Yes.
Okay. It's actually just because we can. And by that, what I mean is in order to stabilize the overall false positive rate, we care about the distribution of fingerprint lengths across the whole filter. Now, the issue is that once you've actually inserted a key, you've hashed it. And once the key is hashed, you can't get any more hash bits for it, right? So basically, once you've decided a fingerprint length for a given key, you're stuck. So if we're trying to do anything, does that make sense?
It makes sense. I was just wondering, it somehow assumes uniform key distribution in your queries, and if you have other distributions where, let's say, some of the where you increase the false positive rate for those keys, and if these keys are the heavy hitters in the queries, then this might not be good. Therefore, I was asking, maybe you can just rebalance based on query key distribution.
Okay, so I think what you're asking about is I think you're making the point that for the older entries in the filter, they have shorter fingerprints,
Yes.
right? And then you might think, okay, the false positive rate for these entries is higher, so that's bad, right?
Yes. Yeah.
Okay, so that's actually a question that I get every time I do this presentation, and it's a very good question, but actually the premise of the question is actually wrong. And the reason is that if you're querying for an old entry that has a shorter fingerprint, if you're querying for an existing entry, you're always going to get a true positive anyways.
Okay.
Right? So basically, when we're analyzing the false positive rate, we only care about, given a non-existing key, what is the probability of a collision? And then the only thing that matters is what is the proportion of entries with smaller fingerprints in the filter, rather than specifically which one it is. So actually what I'm saying by all of this is that this is robust to workload. So
Yeah.
we cannot attack by issuing query for the entries.
Okay, got it. Thank you.
Thank you.
All right, I think we have time for one more question.
So maybe from our end, one question regarding the like a baseline. How does it compare to Bloom filters or fingerprinting in the traditional sense?
Yeah, good question. So first of all, I didn't show these figures in the presentation, but the figures are in the paper. So we did those experiments. In comparison to Bloom filters, okay, first of all, in comparison to traditional fingerprint filters, it's about the same, right? Because with traditional fingerprint filters, it's constant time, and we're still a constant time data structure, right? So with respect to fingerprint filters, it's about the same. With Bloom filters, it really depends on which kind of Bloom filter you're using. I would say that if you're using the traditional Bloom filter, which has many hash functions and every key can hash to totally random bits in a large bitmap, that's actually a very slow filter because it's doing a lot of random memory accesses. If you're using more cache optimal, blocked Bloom filter, there are many papers about how to optimize filters for cache efficiency. And actually, the implementation of filters in RocksDB, for instance, is really cache optimal. If you're using a state-of-the-art Bloom filter that's really cache optimal, I think the Bloom filter will actually be faster if you're using the best and greatest. However, the problem with Bloom filters is that they're static, right? So I think they'll always be faster, but they don't support deletes and they're not expandable. So if you need these features, you need to, right, use something dynamic.
Okay, thank you.
Actually, one final question, Niv, if I may. So have you like implemented this into any system already? Like, say, is this useful for RocksDB, which I know you worked on, or any other system like that?
Yeah, thanks for the question. So when we wrote, yeah, so so the answer is that in these particular two papers, the answer is no. But then in the range filter papers that I talked about at the end of the presentation, right? These range filters leverage these expansion techniques. And we actually took those range filters and applied them on top of WiredTiger, which is right, this B-tree based filter. And there we were really trying to actually, kind of sell the fact that these are dynamic filters, right? So that's why they can work for a B-tree, because a B-tree is not like immutable like an LSM tree. We're also working on some other projects to do with key value separation in LSM trees that uses some of these techniques as well. So some of the work has been done, and we're working on some other threads there.
Well, thank you so much. Let's thank the speaker.
Thank you so much for having me. Really a pleasure to get
Thanks
to
for
know you.
joining, and see you at SIGMOD.
Okay, see you in a month at
Okay.
Sigma. Bye-bye.
See you soon. Okay, goodbye, everyone. Gonna meet again in 2 weeks' time. All right, bye.